Welcome everyone to the final video in the final section in the final chapter of Math 234. Again, we're talking about the divergence theorem here, and this video, right, the subsection I guess is called I Demand Proof. Right, so last time we talked about the divergence theorem and how it is an upgrade from the Green's theorem. But the claim is there are natural upgrades that you would probably suspect that work, but that don't work, right? So you actually have to verify that even though it's a natural upgrade, we should still verify that it works, that it makes sense. You know, maybe we upgraded incorrectly, right? We still need to think a little bit about the proof of this thing. Okay, so the divergence theorem, again, here's the statement of the divergence theorem. We've already looked at this and used this a few times. Let's talk about the idea of the proof here. So I'm going to give kind of a more rigorous proof than I normally do. Sometimes we just kind of think through these things and that's our idea of the proof. But I'm going to go through this a little bit more rigorously. So again, those who are pursuing a degree in mathematics, you should pay extra attention to this proof technique because this actually comes up. It's a common technique that we use kind of over and over again. And here's what we're going to do. So first off, we're going to go ahead and prove it in a special case. So we're going to do a proof in a special case. So some sort of special situation. And then I'm going to talk about how to upgrade, right? We're going to expand this special case to a more general region. So one of our restrictions in the special case is we're going to have a very specific type of region. And then we're also going to expand the special case into a general vector field. So one of our restrictions for our special case is going to be a very specific vector field. So we're going to do this special case, and then we're going to expand. We're going to do a more general region, and then we're doing a more general vector field. And that's going to be the strategy of the proof here. Okay, so the proof of our special case, this is the one that's going to take all of our time really, is we're going to consider a vector field which is rather boring, all things considered. So the first component is 0. The second component, 0. The third component, well, that's where we have the freedom. That's just going to be our normal old r, right? And r can depend on x's, y's, and z's, right? This is just, it's the third component. But those first two components are both going to be 0. Now, that's a very special case, right? Most vector fields do not have zeros as their first and their second component, right? They'd have like p's and q's or something like this. Okay, so this is indeed a special case. Now, our region is special again because it's going to be vertically simple, which is a new term, vertically simple. So I need to tell you a little bit, what do I mean by vertically simple? So E is called vertically simple if, 1, E is bounded on top by some explicit surface, right? Z is a function of x's and y's. And on bottom by some explicit surface. Again, Z is a function of x's and y's, where x and y for these surface are over the same planar region D. And then 2, so it needs both of these things. So we need both. So that's the first condition. The second condition, E includes all line segments from Z1 at some specified point, x naught, y naught, to Z2 at that specified point, x naught, y naught. So these are going to be straight up and down line segments. So let's go ahead and draw this because this is rather confusing. So let's go ahead and maybe draw our nice axes over here, x, y, and z, and I'd like to show you an example of a vertically simple region. So first of all, it's bounded on top by some nice explicit surface. So I'm going to go ahead and try to draw some nice explicit surface here, something like this, and I'll go ahead and shade this in as best as I can. So this is going to be my Z2. It's bounded on top by Z2, and this depends on x's and y's. And now it's bounded below by another surface, right? Z1. And again, these don't have to be, you know, flat planes or anything like this. So I'm going to go ahead and do them kind of interesting like. So maybe this is Z2. Again, let me go ahead and shade this in. So this is our bottom surface. Z1. Again, it depends on x's and y's. And kind of both of these lie over, right, the same kind of planar region, D. So maybe I'll go ahead and do this in purple then. So maybe this planar region here, again, this is going to be in the xy plane, something like this. So this is going to be D. They lie over the same region D here in the xy plane. So that's the setup in part 1 For part 2, right, it includes all of the line segments from some x naught, y naught on z1. So if I go ahead and choose a specific point, so here's a point right here, right, and this is going to be our point x naught, y naught, right? It includes the vertical line segment that goes up here and then to z2, right? So from our surface z1 to z2, same point x naught, y naught. So this is going to be, again, kind of x naught, y naught. But of course, it has a different height here, right? Okay, so it contains all of these points. So it's a lot of up and down things, right? So it looks something like this, maybe. And there, something kind of like that. Hopefully you can kind of get the picture. So again, this is a solid in space, right? So you also include all of the interior and stuff like that. This is a solid in space, but you kind of think of it, it's made up of a top surface, it's made up of a bottom surface, and then it has these sides, right? And everything inside of it, right? Because again, it is a solid region. Okay, so again, our special case deals with this very specific vector field, 0, 0, r, right? And then E should be vertically simple. So it looks something like this. It's bounded on top by a surface, it's bounded below by a surface, and right, and then you can smash into the same region D, right, if we were to get rid of our Z's. So now I'm going to go ahead and I'm going to work with this right-hand side for a little bit and see what kind of simplifies down. So let's go ahead and work with that. So first of all, if you were to go ahead and take the divergence of f, right? So again, here's our triple integral over E, and the divergence of f. Well, again, in our special case, you would take the partial derivative with respect to x of 0, the partial derivative with respect to y of 0, and then the partial derivative with respect to z, all right, of r, right? And you would add those all together. So you would have 0 plus r sub z. And again, this is a triple integral, so it's going to be like dv here. And now let's go ahead and like imagine if we were to start computing this a little bit, right? So if I wanted to start computing this, let's go ahead and do my triple integral here. And this is going to be r sub z. And maybe let's go ahead and choose an order of integration. I'm going to choose our favorite order here. I'm going to do dz, dy, dx. Okay, and if this is the case, right? If I'm doing dz, dy, dx, my first order of business is to do a z integral, right? And so imagine if I have a nice, again, this is a vertically simple region here, and if I'm traveling upward, right, the way that I enter in through this region is through z1. So I'm going to go ahead and say that for my z integral here, I know that I enter in through z1 of xy, and then I exit through this top surface right here, that's z2, right? Again, this depends on x's and y's. So I enter through z1 and I exit through z2. That's the advantage, oops, that's the advantage of using a vertically simple region in this case. Okay, and so the last thing, I would like to go ahead and evaluate out this z integral, right? Because here I have the partial derivative with respect to z. If I then integrate with respect to z, right, differentiate with respect to z, integrate with respect to z, right, these things perfectly cancel out. And so we're going to have a double integral, right? After I integrate with respect to z, there are no more z's. So this is just going to be dy dx left over. Probably have not given myself enough room. Let me go ahead and use the magic of technology here. Okay. And so again, if I integrate with respect to z here, well, I'm just going to have r. And remember, r's depend on x, y, and z, right? So there is a z component here. But now if I was to go ahead and plug in, right, this specific value, right? So I have these bounds. So in the first case, I'm going to plug in z2, right, because that's my upper bound. So z2, which depends on x's and y's. And then I subtract away r of x, y, and now everywhere I see a z, I'm going to plug in z1, right, whatever that surface happens to be. So z1 in terms of x's and y's. And now again, after we've smashed down, right, and there are no more z's in the world, right, we're going to be over this region D. Right, so this region D in the xy plane. So this is going to be the double integral over D. Okay, so this is where we're going to pause, right? And so I expanded the right-hand side of the divergence theorem. Now I'm going to go ahead and expand the left-hand side of the divergence theorem. So again, the left-hand side of the divergence theorem, let's go ahead and start expanding this a little bit. So again, now we're doing a surface integral. So before we were doing the solid region, now we're just doing the surface, right? Which is all of the stuff kind of on the outskirts of this region. So there's a top component, there's a bottom component, and there's a sides component, right? And so let's go ahead and write that down. So our surface is really built out of three things. So we're going to have the double integral over our surface on the bottom. So I'm going to go ahead and do bottom, again, of f dot n ds, plus we're going to have the stuff on the sides of f dot n ds, and then finally the stuff on top, f dot n ds. And I break this up into these three components, right, because the normal vectors are going to be very, very different on these three pieces. And so it makes sense to kind of go ahead and break this up. Okay, so if I was to go ahead and focus on the bottom for right now, right, focus on the bottom. So this is going to be double integral. Again, I'm just going to denote this as bottom for right now. You can use B's or something like this if you'd like. Our vector field is, again, this very special one. It's 0, 0, r, right? And now our n, in this case, right, our normal vector, again, this is a nice explicit surface down here, right? So it's something like this z1. It's a nice explicit surface. So if I want the tangent vector to this nice explicit surface, right, it would normally be, there we go, plus or minus, and then it'd be the partial of that surface. So in this case, the equation is z1 with respect to x, comma, the partial of z1 with respect to y, comma, -1, right? And then this is going to be something like dy dx. Okay, and now we should ask, do we want the plus or the minus? Well, it should be oriented outward, right? So if I want to be oriented outward, then on this particular part on the bottom, right, I want my normal vector to be pointing outward. So again, if I'm on the surface, I want it to be pointing outward, out of the surface. So it should have a negative z component, right? I want a negative z component. And so if you have a negative z component, right, well, again, I already see a -1 here. I like that. So I'm going to choose the plus here, so that way I retain my -1. So I'm just going to go ahead and erase this here. Oops, took out a little bit more than I wanted, to keep that negative component there. All right, so I'm starting to simplify the bottom. Let's go ahead and start to simplify the sides, right? So if I go ahead and start simplifying the sides here, so again, our f is going to be 0, 0, r, and then I need to think about our normal vector in this case. So again, let's go back to our picture. We're going to get a lot of mileage out of this picture here. So if I'm on the sides here, and I'm thinking about a normal vector that's, again, pointing outward sort of deal. Outward, outward, right? Any of these can be normal vectors here. The big thing here is because the sides, right, they kind of move, they're straight up and down, so the normal vector is not going to have any z component, right? These are going to be functions of x's and y's, but z is going to be able to roam free, right? It goes up and down kind of willy-nilly. So again, there's not going to be any z component. So this is kind of hard to write down exactly what the components of x's and y's are going to be. So it's just going to be some complicated thing with x's, some complicated thing with y's. But then the big thing here is that the z component, again, z is roaming free. There's not going to be any z's. So if you were to take a partial derivative with respect to z, for instance, you would get out 0. And now this is very, very nice, right? And so the sides here, again, I'm going to go ahead and technically put dy dx. That's not so great. Actually, let me just put dA here. Because again, this will be some double integral over a region. Okay. And actually, maybe you can already see where I'm going with this, right? When you take this dot product, 0 dotted with anything, right? So times anything is going to be 0. 0 times anything is going to be 0. And then r times 0 is going to be 0. So this part's going to perfectly go away, right? This is just going to be integrating 0, which will end up being 0. Okay, so the sides part will go away. Now, let's go ahead and integrate the top, right? We've done the bottom, we've done the sides. Now let's go ahead and do the top. Again, our vector field 0, 0, r, and then we're going to dot product along with, again, z2. Again, so we're going to have this plus or minus. So let me go ahead and do plus or minus. And so this is the normal vector here to z2. So it's going to be the partial of z2 with respect to x, the partial of z2 with respect to y, and then -1. Again, this is back from our a long time ago, 14.4. We talked about the tangent vector, the normal vectors to the tangent plane to a surface, right? So that's what this is here. And now this is going to be, again, dy dx. Let's go ahead and choose our normal vector, right? Do we want the plus or do we want the minus? Well, for z2, we're up here, we would like our normal vector to be going outward, right? So in this case, outward is the same thing, right, as upward, right? We want it coming up out of this surface, so that way it's away from kind of the inside of this region. So we want to have a positive z component. So if I want to have a positive z component, then I would really like this -1 to be a positive one. So I'm going to go ahead and choose that negative right there, so that way when I distribute it to each piece, right, I'm going to get a +1. So let's go ahead and do this distribution here. That'll be the last thing before we kind of do more steps. So, oops, I took out a little bit more than I wanted. So if I distribute that negative, here's a negative, here's a negative, and here's a positive. So let me just go ahead and write +1 here. All right, so this is going to be the negative partial derivative of z2 with respect to x, the negative partial derivative of z2 with respect to y, then +1. Ugh. All right, I promise we're getting close now. So again, let's go ahead and start combining these things. We have the bottom, and if we do the dot product here, we're just going to have -r. Now remember, r here, it depends on x's, it depends on y's, it depends on z's, right? And that's going to be dy dx. Then we have the sides. We already talked about, right, the dot product here, we're going to have 0 times anything, 0 times anything, anything times 0, right? When we add those all together, 0 plus 0 plus 0 is indeed 0. So this part's going to nicely be 0. And then finally we have the top. Oops, sorry, I forgot my dx back here. I have a dy and then I need a dx. There we go. And then finally the top, and let's see, if we go ahead and do 0 times, who cares? 0 times, who cares? R times 1, well, that's just going to be positive r. And again, r depends on x's, y's, and z's. And this is going to be dy dx. Good. So the last thing is that when you're on the bottom, right, again, there shouldn't be any z's here, because this is an integral with respect to y and x. Again, z's kind of been killed off. We don't have any z's here. And so we need to go ahead and replace that, right? Instead of z's, we should go ahead and replace that with x's and y's. Well, which x's and y's should we replace it with? Well, it depends on the surface, right? And we should use the surface's function. So we should use, right, z is equal to z1 of xy, right? Some function in terms of x's and y's. And likewise, up here, z is equal to z2 of x's and y's, right? So it depends on where you are in terms of x and y. So let's go ahead and replace that here. So this is going to be the double integral over the region D of -r of x, y, and again, everywhere I see a z, I'm going to go ahead, we're on the bottom right now, so that's z1 of x's and y's. Good. Now, dy dx, forgetting this d here, dy dx, there we go, plus the double integral over d of, again, r of x, y, and everywhere I see a z, I'm going to put z2, right? So that's the function's equation on the top, right? Again, this is the top surface. Okay, dy dx. And maybe the final thing, man, I'm horrible at writing dx's these days. Dy dx. There we go. And now the final thing is that we have two double integrals and they're over the same region D. Right, so they're over the same region D. We can go ahead and put dy dx out here. And so if we were to go ahead and combine these things, right, and let's do the positive one first. So I'm going to do r of x, y, and then this is z2 of xy minus r of x, y, z1 of xy. And if you remember, right, if I go ahead and maybe highlight this here, take a good look at this, and then compare it to this up here. And notice that they are the exact same. right? So, and this was, right, originally we started with the right-hand side. We worked down a little bit, we got to this point. Now over here, right, we started with the left-hand side, right, the surface integral of f dot n ds. And this one took a little bit longer to work with, but we got to the same result, right? So they're both equal to the same thing, and therefore, right, they have to be equal to each other. Again, we're trying to prove that in this very specific situation, that the divergence theorem holds true, right? That we get this good result. All right, so that was the proof of the special case. So we have now done number one here. We have proved this special case, right? If we have, a nice vertically simple region and we have a relatively simple vector field, right, we can prove this. So the question is, how can we expand this to the more general case, right? Because this isn't just a statement about vertically simple regions over very restricted vector fields, right? We can talk about any old region and any old vector field. So how do we do 2 and 3? How do we expand this to a general region and a general vector field? Okay. And so the idea here behind number 2 is that really any region out there can be decomposed into a bunch of vertically simple regions. So any region that you have, we could just break it up, right? We could break it up into a bunch of vertically simple regions. Okay, so maybe to demonstrate this, let me go ahead and draw a nice donut. So I'm going to draw a donut something like this. This is more, typically called like a torus or something like this. And so in order to break this up into a bunch of vertically simple regions, I'm going to go ahead and make some cuts, right? So I would make this is not at all how you would normally cut a donut, but okay, we can do it here. So I'd go ahead and cut like this and like this. And the claim is this piece right here is now a vertically simple region, right? So they both lie over kind of this region D, right? And kind of above by, this would be our Z2, and below by Z1. So there's maybe our first piece. Now I would also make cuts over here, kind of in a similar fashion. And again, now this piece over here is vertically simple. So we could take something like this, and now again, they're both over the same region D. Oops, wanted my highlighter here. Same region D, and over this region, right, this would be the Z2, the surface on top. This would be the surface on bottom, Z1, right? And then we would have finally maybe this top piece, something like this, and kind of at some point, right, there's going to be this like natural break. So something like this, perhaps. So that's along the front. We could also do one kind of along the back here. And kind of on top, there would be Z2. And on bottom, we would have Z1. And now maybe in the XY plane, they would both lie over, maybe we have to draw it in the XY plane, but they both lie over something like this in the XY plane. And then finally on the bottom, right, again, there's going to be kind of this natural, you can do a break kind of at the thickest part of your donut here. So something like that. And again, there's going to be a Z2 on top and a Z1 on bottom. So we can just break this up into a bunch of components, right? A bunch of vertically simple components. And again, maybe this would be over the same region in the XY plane as the top piece was, this piece right here. Okay, so this is how you would kind of decompose, for instance, a donut into 4 vertically simple regions. So kind of, if you want to do kind of a more general case, right, the claim is, well, just break it up into these vertically simple regions and then compute the surface integrals and the triple integral over each one of these vertically simple regions, right? Then add it all together and you'll get the same result. All right, so that's how we can upgrade regions, right, from vertically simple regions to any old region, right? It's just by using this trick. Now finally, number 3, right, I want to tell you how to expand, right, the special case, right? We had a very specific vector field, 0, 0, R, right? And we want to be able to expand this to a more general vector field, right, with P's and Q's and things like this. And so, okay, if you wanted to do that, let's go ahead and do, right, PQR, like the normal vector field here. And if you were to go ahead and compute this out, right, we can take the dot product with our favorite normal vector here, n1, n2, n3, do that out, and then we can go ahead and break up the surface integral kind of into these three pieces, right, because we can go ahead and add each piece together, and kind of, or you can think of this as distributing the double integral, right, the surface integral to each piece. And so that's how you get this, right? And this was one of these rules for double integrals, triple integrals, surface integrals, line integrals, kind of, it works for all the integrals. Likewise, you can do this for the triple integral, right? If you were to calculate out the divergence of the general f, right, it has p's, q's, and r's, you would get this. And then you could go ahead and distribute this triple integral to each piece, and you'd have something like this. And so in our case, right, we already dealt with this special situation right here. We went ahead and we showed that this third case, if you have r sub z dv, right, this is equal to the surface integral. So let's go ahead, right, on the second page, I actually specify this, I have it written down. So we've already shown that this surface integral of r dot n sub 3 ds is equal to the triple integral, right, of r sub z dv. Now we can do very, very similar proofs, right? It would just kind of take, we'd have to do it for another 20, 30 minutes or so, showing, basically exactly the same work right here for these other two special cases. So, but with this same work sort of deal, we can go ahead and show these results. We can show that this surface integral of over S of Pn1, so this is the P component, ds, is equal to triple integral of P sub x dv. And we can show that the surface integral over our surface of Qn2 ds is equal to the triple integral over E of Q sub y dv. And so yes, it would do very similar proofs. Instead of splitting these up with vertically simple regions, right, this one right here, you would split it up with kind of horizontally simple regions, right, in the x direction. And likewise, here you would split it up with horizontally simple regions in the y direction, right? So they are slightly different, but with the same idea, we can come up with the same result. All right, so that is why the divergence theorem works. Again, this is in the general case. We did it for kind of a very specific case, and then we expanded to a general region and a general vector field. So like I mentioned up here again, kind of if you're thinking about becoming, a math major, this is a common technique for some of these big proofs, right? They are difficult, so you show them in a very special case, and then you make upgrades. All right, that's all there is to it. We'll have some more examples in class. I'll see you then.